So the next talk will be by Pierre Simon on finitely generated dense subgroups of the automorphisms.
Okay, thank you. So thanks a lot to the organizers for inviting me. It's been a great conference. So I'm going to talk about a theorem on automorphism groups of omega-categorical structure. So the theorem will give some condition for such a group to have a finitely generated dense subgroup. So it's a small question that came up at the conference a few months ago. So it's all joined with Itay Kaplan. And I hope to be able to give you the proof, or at least a sketch of the proof. And yeah, I'm also hoping that maybe some ideas in the proof could be useful for other things in the study of omega-categorical structures. So let me start by the context. So Catherine, in her talk, already gave some basics. I'll repeat some of them. So if you have, so first maybe you have S infinity, which is the group, the symmetric group, the full group of permutation of countable sets, and this is has a topology where the basis of open sets are given by if you have two tuples A and B of the same size, you have you can look at the basic open set of the elements of S infinity, which send one to the other. So this makes it into a topological group. If you have a countable structure N, then you can associate to it its automorphism group. And if you, since N is countable, if you view it as, if you view its universe as being in bijection with N, you can see this as a subgroup of S infinity, and as such it's going to be a closed subgroup. That's not hard to see because preserving the structure just amounts to not sending sending tuples to tuples of the same type is a finitary condition. And conversely, if you're given a closed subgroup of S infinity, then it is the automorphism group of some countable structure. Of course, in general, you cannot recover the structure from the automorphism group. Many very different structures have trivial automorphism group. However, if the structure is omega-categorical, then you can. So omega-categoricity here corresponds to a condition here that the group is oligomorphic. So oligomorphic for a group acting on a set means that there are finitely many orbits on n to the n for all n. And so this is, and then if you have a closed oligomorphic subgroup, so it's the automorphic group of some omega-categorical structure, and you know the structure from the group up to by interpretability. So essentially the study of omega-categorical structure is very group theoretic. Sorry?
What?
Did someone say something? Okay.
From a topological group. You know it as a topological?
Yeah.
As a topological?
Yes.
Yes. Oh yeah, thank you. Yeah. Yeah, thank you. Yes, it's an area that's it's at the border of model theory, group theory, descriptive set theory. Probably in recent years, the most interesting progress came from descriptive set theory. I won't talk about that. This will be sort of softer. I'd like to point out, so let's call G, call G this group. that the same way that closed subgroup correspond to structures, if you have
The mic is off.
It's basically the you have a loud voice anyway, so it's actually.
you think so?
I think possibly.
Okay, but you're not sitting in the back row.
Yeah.
Yes.
Okay, so this is without the mic.
Fantastic.
If you keep talking like this.
Beautiful voice.
Is everybody okay? Okay,
No,
good.
no, it's not. Please use the mic.
Okay, let's see how it goes. So if you have a closed, if you take your group G, which is alt n, and you take a closed subgroup of it, then this corresponds on the other side to taking an expansion of n. So I don't know how to write expansions, but this will be, so if this is closed, then this will be alt m prime, where m prime is an expansion of n. Okay, so and conversely, every expansion, if you have an omega-categorical expansion, it corresponds, or for that matter, any expansion.
Excuse me, does
Its
anything
automorphism
special,
group will be a closed subgroup.
anything special happens if it's log log?
Yes, what does normality mean? I need to think for a second. Maybe someone can answer. It's easier for. Okay.
There was a different consideration in mind.
It's hard to think in. Yeah, I need to think about this. But yeah, I think it means that the expansion is.
Is what?
Okay. It's not. In general, that's not going to happen.
So here what you are
I
saying
need to
is
think
that
about if it ever.
you are saying that if H is a closed subgroup and if it is odd M prime can be chosen to be substructure of expansion of M? Always?
Yeah, that's the point.
Yeah.
Yes.
Yeah, always.
Yeah, because this is.
Okay, always.
Okay, so what are examples? Some examples that I will need are very basic. So of course, the most basic example is just n with equality, and then the automorphism group is simply the full symmetric group. Slightly more interesting is ELO. You also have one thing that will come up is the circular order. So the circular order, it's a circle, and you have a ternary relation x, y, z, which tells you that 3 points x, y, and z are in this, or in say the direct order on the circle. So you probably also know the random graph, which is also a binary structure. And also something that might come up are trees. So a tree is a partial order such that below every point you have a chain. Below every point the order is linear, and the model completion of, or the phrase, if you want, limit of all trees is omega-categorical. It's the infinitely branching tree where each branch is dense. Okay, so those are the structures you can have in mind. Right, so in group theory, when people study, say, finitely generated groups, so if you have gamma, a finitely generated group, you might want to ask, something you want to do is understand its actions. And one question that you could ask is, does it have an oligomorphic action? So you could ask the question, does gamma have an oligomorphic action? I don't know if it should be raised. on a countable set, what does this mean in our terminology? This is equivalent to, is there an omega-categorical structure such that gamma can be seen as a dense subgroup of the automorphism group of M. So you need to think for a minute to see that what does it mean for a subgroup to be dense? It means that it has the same orbits. So because it means that if the full group sends A to tuple A to B, then also there is someone in gamma that already sends A to B for any tuple A. So it means that gamma has the same orbits on M to the N for all
But there
M.
is a faithful action of this gamma on M?
Yeah, okay, yes, right. So yes, a faithful action. Does it have a faithful oligomorphic action? Yeah. Yeah, thank you. So this is the same as saying if you can embed gamma as a dense subgroup of some oligomorphic group. So this is some question that comes up when you want to understand groups. And for us, it's natural to reverse the question, to sort of ask, given an omega-categorical M, you might ask, what are its, and here you can say maybe finitely generated or countable dense subgroups. What are of odd M? And then, of course, the first question you could ask is there actually a finitely generated dense subgroup? So having a finitely generated dense subgroup is usually called having finite topological rank. So, okay, so this is the question I want to address. And so first, well, a basic example, let me give just one. So it is known that most of those structures had two generated dense subgroups. So, for example, for S infinity, if you see S infinity as the automorphism, instead of N, let's take Z, then you can generate a dense subgroup by taking a shift and a two-cycle. So you can check that this generates a dense subgroup of S infinity. So two generated dense subgroups tend to exist, and in fact we'll see that in most omega-categorical structures they do. Where most is not defined in any reasonable way. But I guess understanding if most really means most is will be one of the open questions. Yeah. Okay, so there is one obstruction. In fact, this is the only really known obstruction to having a finitely generated dense subgroup. It has to do with compact quotients. So if you have M omega-categorical, you can look at ACLEQ of the empty set. Okay, so there's the set of elements in EQ that's algebraic. And you can consider the automorphism group of that, let's call it K. So K is a compact even profinite group. And if you have if you take odd n, then if you have an automorphism of M, it induces an automorphism on ACLEQ of the empty set, so you have a surjection from your group to this compact group. And one can show, I don't remember who proved it, that any profinite group can appear as in such a way. And in fact, K, one can also see that K is the maximal compact quotient of G.
continuous map, right?
So maybe I'll call the kernel G0.
Yes.
What?
Okay. This is continuous map.
Yes, yes.
Parallel is normal and closed.
Exactly, that's one example, yes. it might be the only one, yeah, it might be the only one.
No, it's not.
Okay, okay, I don't know. Well, someone will answer maybe at the end. Right, so this is the maximal compact quotient of your group. And if you have a finitely if you have a dense subgroup here, it will map to a dense subgroup here. If you have finitely generated, it will give you a finitely generated subgroup here. But K, not all cofinite groups have finitely generated subgroup. For example, if K is the product of something Z over 2Z, that doesn't have finitely generated dense subgroup. And it's also worth noting that this G0 here, which is the kernel of this map, is closed, and so it is the automorphism group of some expansion of M, which is actually omega-categorical. So really, you should reduce all questions to studying this guy, and then G will be, I mean, on K you can say nothing. You can just assume that it's topologically finitely generated, but we might as well assume that K is trivial, and just work on G0. Okay, so that's one obstruction. If you have a K like that, that's not topologically finitely generated, then the group isn't. And it's the only known obstruction. So we don't know if we don't know if this is a necessary and sufficient condition.
But there's also the general last argument, wasn't it? There's also the general last argument, I mean, which
Yeah, but this is omega-categorical, so
no, it could be,
it doesn't go.
No, it could be different.
Okay, then I don't know exactly what you mean by
And
that.
that's also an obstruction. That's also the general last group is also an obstruction. Yeah, and it need to be the same as that.
But you need some saturation assumptions in there.
Okay, we can talk about it later. Okay, so how to find, how to get the two generated then subgroup? So what I will give now is a sufficient condition. I'll give it in 2 steps. So definition, okay, so first maybe a notation. If I have 2 subsets of M, I will write A is non-splitting independent from B if some of the type of A over B and the type of B over A are invariant. So if whenever you take A prime in A, B prime in B, then A, B has the same type as A prime, B prime.
What are the additional assumptions?
That's the definition. Oh, of course. A has the same type as A prime, B has the same type as B. Thank you. There were some additional.
What's the symbol N? What's the symbol N?
NS.
NS for non-splitting. There'll be another one, so I need to write it down. And we'll define an automorphism. We'll say that is repulsive if it sends finite sets to independent ones in this. So if given for any finite A in N, there exists an N such that A is non-splitting so that sigma n of A is independent from A in this sense. So you can push finite sets far away to things that are independent. So let me give you an example. If you're in DLO and you just take sigma to be a shift, where I view DLO as the automorphism group of Q, you take sigma to be x goes to x plus 1, then if you take any finite set, if you iterate sigma sufficiently, the image will be disjoint from it, and then those two things are, so what does it, yeah, another way to see this condition, it means that if you have a partial automorphism acting on A, you can extend it by the identity on B, and conversely. So here, if you have a partial automorphism on A, say you send those 2 points to those two, you can extend that by fixing those pointwise. So this is a typical example, and the examples we'll give of repulsive are of this form, somehow, or some kind of generalization of this. Okay, so the first proposition is that if you have a repulsive automorphism, then you're good. So if sigma is repulsive, then there is some f in odd n such that sigma and f generate a dense subgroup, but it's even slightly more than that. It's that such that sigma n f sigma n minus 1 is dense. So the conjugate, this is called the cyclically dense conjugacy class. So f has a dense conjugacy class, and even you just need to conjugate by powers of sigma. And this was known, I mean, it was known for all the basic examples that, like, yeah, well, I haven't yet stated that things like DLO and the random graph have such things. I'll do that right after, but it was already known that they did, this notion. The proof is quite short. The idea is the main thing is to understand what this means. But so essentially, if you're given a partial, so the idea of the proof, I don't know how many details I have time to give, but so the idea of the proof is you build f by back and forth somehow. It's not exactly back and forth, but or by induction. I don't know how to say. So you enumerate a countable basis of neighborhoods of odd m, and say you've already built f, some partial f. So you have some partial f that sends some tuple c to a tuple d, which are finite at some finite stage of the construction, and you're given a basic open set. So the set of elements that send sigma, the set of sigma that sends A to B.
Tau. Sigma is there in the right.
Thank you. Well, now this looks like.
Yes.
This is a tau. This is a So imagine you're given some open set, and what you want is to extend F0 so that this thing will hit that open set. And for that, you pick n. You pick n such that C, so I need to get it right, CD is independent from sigma n of AB. And then this non-splitting condition exactly tells you that you can extend F0, then if you extend A0 by sending A to B, this is a partial automorphism.
Why does this n exist?
By hypothesis on sigma, because sigma is repulsive. This is exactly what repulsive tells you.
So you take A equal to A, B, C, D. Okay.
Yeah.
Oh, right. Yes. Yeah. Yeah, I could have stated the disymmetric condition. Okay, so this is the proof. Then you do this for a countable basis of neighborhoods. So now the question is, how do you get repulsive automorphisms? And here we don't have we have one condition, which will be in terms of having some kind of independence relation on your structure. And this we'd like to understand more about it, but we don't know that much. So what do we need? So definition. So independence. So this is a relation that has three, which means this is independent from this over this. So it's a ternary relation on subsets of M, say, or even maybe on the monster model. I'll call it canonical, which is probably not a good name, but let's keep that for this talk. If it satisfies the following conditions, so there are some.
On the left, didn't you mean sigma NA goes to sigma, on the left board before, sigma NA goes to sigma NB? Because otherwise it doesn't seem like this N plays the role.
You're absolutely right.
Yeah. Okay.
Thank you. Yeah, so this will not be in this set, but the conjugate by sigma n will. Yeah, thank you. So I extend it like this. So what we ask for are, so first there are basic things that I won't spell out, like existence, extension, subset, and they might not be the strongest form of those, but okay, they're not so important. There are two conditions that are the important ones. This is stationarity and transitivity. Stationarity over the empty set, which tells you that, well, if you have A independent from B and A prime independent from B prime over the empty set, and A has the same type as A prime, B has the same type as B prime, then AB has the same type as A prime B prime. So there's a unique way, it just tells you uniqueness if you want to see something. There's a unique way to amalgamate, to put two tuples freely over the empty set. And the other one that's a bit more mysterious is transitivity. It's sort of the difficult one to deal with, to understand, which says that, so this is the usual, so we want transitivity on both sides. So if A is independent from D over DC, and D is independent from C over B, then AD is independent from C over B, and you have it on the other side also. So I'll just write it down. Okay, so you have transitivity on both sides. Let me give you some examples of such things.
Sorry, what's the difference between the stationarity and the non-splitting independence?
Yeah, yes, that's a good point. So stationarity implies non-splitting. So stationarity tells you that this relation implies non-splitting, but it says more because it says you're choosing a non-splitting extension. It's possible that with the other conditions, I'm not sure. So it says that it's not only that they don't split, but you control the complete type of the pair. Right, here I have two pairs of independence. In stationarity I had only one, so slightly different. So this is stronger. So yeah. So examples. But if T is stable, if your theory is stable and ACL, EQ, and types are stationary over the empty set, then you can just take non-forking. Actually, to be fair, we only need transitivity over models, where the bases are models. So those are not somehow optimal conditions. But. Okay, perhaps more interestingly, if you take DLO, then you can take, well, over the empty set, you can just say that two finite sets A and B are independent if A is less than B. So if you have two finite sets A and B, you say they're independent if A is entirely before B. And if you have a base, then you need to say that in every cut of the base, all the elements of A are before all the elements of B.
So there's no symmetry in your...
Right, so yeah, that's a very good point. Those things have been looked at before by various people, including, I guess, Catherine Tent, and Martin Ziegler, and McPherson, etc. They assume symmetry in all those reasons. So if you assume symmetry, you have very strong theorems that follow. But the main thing is that we don't assume symmetry here. So we have a chance of finding those things in a lot of structures. In fact, I don't know really of any, well, I'll come back to this, but in some sense, I don't know of any structure that really doesn't have such a relation in some sense. So for DLO, you just place, yeah. So of course, you could choose the other one. You could choose to place B before A. So this is where stationarity is stronger than unsplitting. You have to choose one of the two and stick to it. If you take the random graph, then you can say that A and B are independent over C. And here again, you have two choices. You can say if you don't have any edges between A and B except those that come from C. So you have so if there are no edges between A set minus C and B set minus C. So you amalgamate two things by simply doing what's called a free amalgamation by putting no relation on them. You could also choose to put all edges. That will also be fine. But you have to choose one of the two. Okay, so this also has such an independence relation. Okay?
Are you also assuming the sets don't intersect, like outside of C?
Oh.
Thinking of equality.
Yes. No, yes. I am. Yes, I am. Yeah, you're right. I am. Okay, now the proposition which you might expect is that if you have such a relation, then you have a recursive automorphism. So if n admits a canonical independence relation, then aut m has a recursive automorphism, well, has a recursive. There's a recursive element, there's a recursive automorphism. And the proof is again rather short. What you do is you try to mimic this shift. You try to, so in DLO, the recursive automorphism was a shift. I guess in the random graph it's a bit harder to see, but it would be an automorphism that for any finite set, it sends it at some point, it sends it to something that has no edges with what you started with. So it sort of goes towards an invariant type. And the way you build it is, so you take, we're going to, so m being omega-categorical, it's enough to build this automorphism on any countable structure elementary equivalent to M, which will actually be M, but I can somehow construct it in a different way. So what you do is you start with a copy of M, which you call M0, and then you place an independent copy of N. Say you work, imagine that you work in the monster model. You place an independent copy of M, where independent is according to this guy, next to it, and you call it M1. And then you amalgamate them into one, you find one model that contains both, say M01. And now you copy M01 to the right over M1, so you make something like this to get M12. So you place it so that M01 is independent over M1 from M12. And inside M12 you get an M2 here. And then you complete that into an M012, then you copy M01, you shift M012 to the right, and I guess you also need to go in the other direction. So you build some kind of thing like this, which, okay. And this becomes a countable, when you're done, you have a countable model which you might, which is isomorphic to M. And now you have a shift. You just can define sigma which shifts by 1. So you send M0 to M1, M01 to M12. You can shift this whole picture by 1. Because right, and this sigma works just by the non-splitting, essentially the non-splitting condition of this. If you have a finite set, you iterate sigma sufficiently often. At some point, the finite set will land on some triangle that is joined from the triangle the finite set was in, and then those two are independent. Okay, so that's the construction. Yeah, maybe I should have pointed out, just as a sanity check, that having this condition of stationarity implies that ACL EQ of the empty set is DCL EQ of the empty set, because it implies that you have invariant types over the empty set. So a corollary of the superposition is if you have a canonical independence relation, then you have a two-generated dense subgroup. And this covers lots of cases, but not all. So now let's look at what happens when cases are not covered. Are there any questions? So now I want to look at expansions. So what is a typical case that is not covered by this? Well, the easiest one is the circular order. So if you take a circular order, there is no canonical relation. In fact, you cannot even place 4 points, 2 pairs of points in a non-splitting way from each other. Because if you have, say, A, B, and C, D, and it's not the case. Say they are placed like this, but there aren't many ways to place 4 points on a circle. If you try to place them like this, so in the circular order, you can actually exchange B and A. There's an automorphism that exchanges B and A, which turns like this. You turn B to A and you turn A to B, but you don't do this. You turn around. And if you do this, you're not going to fix BC. You're going to send BC in here.
BC or CD?
CD. Yeah. Here. So there's an automorphism that extends. So A and B have the same type, if you want. A and B have the same type, but they don't have.
A, B, and BA have the same type.
Sorry?
A, B, and BA have the same type.
Right, exactly. Yeah, it was A, B, and BA have the same type, but they don't have the same type over CD. So there's no chance of placing things in a non-splitting way. So the circular order does not have invariant types over the empty set. That's sort of the point. So what do you do here? Well, in this particular case, it's not very hard to get a finitely generated dense subgroup, because you notice that as soon as you name a point, so if you look at the expansion that you get from naming a point, then the automorphism, so let's call this NA, let's call NA the expansion where I've added a constant for a point, then the automorphism group of NA is the same thing as the automorphism group of ELO, because once you fix a point, then this becomes a linear order. So if you're not used to this, you have to think for a moment, but the only thing you can do on the complement of A is to somehow shift it. And so it exactly has the structure of a linear order. And this, we know, has topological rank 2. There's a finitely generated, there's a 2-generated dense subgroup. Okay, so how does that give us a dense subgroup of the full group? Well, I claim that now, if you take any sigma that moves A, then sigma along with the automorphism that fix A topologically generate the whole group. So you only need to add one automorphism to the one given to you here. You take any automorphism that moves A. So if you take any sigma that moves A to some A prime, then I claim that the automorphism group of M is topologically generated by the automorphism group of NA plus sigma. Okay, why is this true? That's not hard to see. I mean, there are several ways, I guess you can see it, but let me give one argument. Maybe I should watch. So let's look at what we get if we add sigma to this automorphism of MA and take the closure. We get a closed subgroup of the automorphism group of M that lies between the automorphism group of MA and the automorphism group of M. This closed subgroup is the automorphism group of some expansion of expansion of the circular order, which is also a reduct of the circular order when you name a point. But because we've moved A to A prime, it's also a reduct of NA prime. Because you also have, if you conjugate by sigma, if you conjugate oath NA by sigma, you exactly get oath NA prime. So now you have a reduct of both NA and NA prime. So a zero definable set in that reduct is going to have to be both A and A prime definable. And then you just see that they all know that the only zero definable sets are both A and A prime definable. So here the main point was that, so that you move A to some A prime so that you don't have a definable set which is both A definable and A prime definable. And then the only thing you are left are zero definable sets. So you get the full automorphism group. And this idea we can generalize a little bit. So in general, if you look at okay, let me say it. So I should say the idea now will be that if we have a structure that does not have an invariant equivalent, a canonical independence relation, we're going to try to look for an expansion of it that does. And the theorem will be that if you can find an expansion of it that's still omega-categorical and has such a relation, then you're good. You might have, it will not be 2, it will be 4, but you'll be good. So let's look at another special case. Say, well, it's not yet in general, right? But say that you have M and you have an expansion where instead of naming a point as here, you name an m-definable set. So you name a definable set, but this set has parameters. It's definable over parameters, so you add it as 0 definable. Then you can do exactly the same game as here. So you say you name an x-definable set x, you can look at the canonical base of x, and you can, well, you don't even need to do that. Let's say x is a-definable, where a is finite, then you can find sigma, which moves a to a prime, such that ACL EQ of A intersect ACL EQ of A prime is just ACL EQ of the empty set. So you move it to something that is independent in this sense of algebraicity, and then if you add sigma, you'll get the full group by the same argument as here, because this guy would be the automorphism group of some structure, and a 0 definable set in that structure will need to be both A and A prime definable. So its canonical base would need to be both here and here, but here is here, and ACL EQ I'm sort of assuming is equal to DCL EQ, because otherwise, well, we've reduced to that at the beginning. So, okay, so this is the first observation on how you can easily go from M to an expansion. But this is not always the case. You might have an expansion that names something that wasn't definable at all. And then you need to do some back and forth. And there's a rather fun argument that I was hoping to have time to give. Well, I might have time to sketch it. So okay, let me now state the theorem that if M has an expansion N with, well, which is, okay, let me not say, take M, omega-categorical, and take an expansion N that's omega-categorical. I'm not going to assume anything about, and I do need to assume that there are no compact quotients around. Let me do it, and so assume, you can be a little bit more general than that, but let me just assume that N has no compact quotient for simplicity. Out of M, yeah. And you don't really need that. What you need is just that out N knows the compact quotient, that it surjects onto it. But assume out M has no compact quotient, then there are F and G in out. So remember, N is an expansion of M. So out N is a subgroup, closed subgroup of out M. And so what I claim is that you always just need two elements to go to the full group. So there are F and G in out M such that out N is generated topologically by out N, F and G. So it's the closure of this group. So as a corollary, if out N has a 2-generated dense subgroup, then out M will have a 4-generated dense subgroup. Yeah, so I don't really have time to give you the construction, but let me just say that the two elements you get, F and G, have a very different sort of purpose in life. The role of F is to take care of expansions like this. So F is an element that will do this, that will make sure that once you add F, the expansion you get, the intermediate expansion you get, has everything that is definable in it over the empty set and definable over M with parameters is actually definable over M over the empty set. So this you can do by doing something like that. And then once you're in this situation, you have some kind of back and forth construction that gives you G. And okay, this, I don't have time to give. Okay, and now, well, the sort of question is, can you always apply this theorem? So, does every omega-categorical M have an omega-categorical expansion with canonical? And if this turns out to be not true, which it probably is, I will of course ask it for finitely homogeneous. Sorry. But I don't know of any example. So what are actually the only examples I know where you really need an expansion are the circular order and the unrooted tree. And things that you build from them. But maybe other people know other examples, but I don't really know much more complicated examples. Okay, so the last thing I want to say is a small relationship with Ramsey. I mean, I'm not going to say much, but there's a question in, so I believe the paper of Wodierski, Pinsker, and Todor-Tsankov, where they ask if you have finitely homogeneous structure, can you find a omega-categorical or finitely homogeneous expansion which has the Ramsey property. So I'm not going to define the Ramsey property, but so I'm going to cheat. So M has Ramsey property. Well, this is really a theorem of Tekris-Pestov-Todarchevich. M has the Ramsey property if and only if all M is extremely amenable, which means that if whenever alt M acts on a compact space, there is a fixed point.
Is this the definition?
No.
So what is the Ramsey property?
The Ramsey property essentially tells you that whenever you act on an expansion of M, you have a fixed point. So for example, if you look at linear order on M, this has a fixed point. But if you look at anything, any extra structure you want to put on M, you'll find a fixed point. So you'll find a zero definable one. This is what the Ramsey property tells you, and this theorem tells you actually if you act on any compact space, you have a fixed point. Yes, okay. But so this is. I just want to point out how those two definitions are different. How those two questions are. They're different. They're completely independent. You don't need the Ramsey property to have a canonical thing, and conversely. But there is some relation between them in that if you have the Ramsey property, then you have an independence relation that is at least stationary. And what is missing is the transitivity. So you don't know if you have transitivity, and there are examples. So if you take an ordered tree, this will be a Ramsey structure where you don't yet have transitivity. You still need to expand it. You still need to name a point to actually get the canonical independence relation. And I just want to say what is last few minutes I want to state a dynamical consequence of having a canonical independence relation, which is not an equivalence, but it's a consequence which shows if you already Ramsey, say, it will tell you what more you need to have such a relation. But it doesn't assume Ramsey. So the proposition, so if M has, actually if M has a repulsive automorphism, sigma, then whenever alt M acts on a metrizable compact space, And whenever you take any point in K, so say, yeah, okay, let me just take it. Then there is a conjugate to sigma, such that if you look at the forward orbit of the point under that conjugate, and you take the closure, this contains a subflow. And same thing for the other, doing the other way. So in particular, let's say your structure is Ramsey. What this is saying, so the Ramsey, this property tells you if I take any point in K, and I look at the forward orbit under the whole group, and I take the closure, it contains, there's a fixed point somewhere in that closure. This is telling you, you don't need to look at the whole group, you just need to take one conjugate of sigma, and look at the forward orbit, take the closure, it has a fixed point in it. So this is, if you already Ramsey, this tells you what more you need. And I don't know what really this means, but maybe some people have thoughts on that. But this is a way to show that something does not have a repulsive automorphism.
For all x.
Yeah, this is for all x. For all x in K, there's a conjugate of sigma, so that if you just look at the forward orbit
And your term is either zero categorical, right?
Yes, always. I mean, some of those things can be generalized to just homogeneous, but okay, so right, so that's all I really have to say. So there are a number of open questions here that I'll just say out loud. So first, how can we hope to find such an expansion? The natural way is you take the space of types of a model over M, and you take a minimal flow of that. I mean, if you have a fixed point, that will exactly give you an invariant type, and it's natural to take a minimal flow of that and ask, and this somehow gives you an expansion of M, and ask if that expansion is omega-categorical. And that would be sort of an attempt to actually construct such expansions in general. I don't know if that works. Another idea is we have this relative statement here, which tells you that this property of topological finite rank goes from expansions down to the structure, or goes up if you think in terms of groups. It would be interesting to prove other kind of relative conditions like that. For example, with the small index property and things like this. Maybe there are other, this idea of course, proving a relative condition is much easier than proving for the full group, because you already have both n in it. So this might be interesting to look at. And also it could be interesting to draw other consequences of having such a canonical relation. So things that have been proved using symmetry, they're not going to hold without symmetry, but maybe some weaker forms could. So I think those are interesting questions to look at. I'll stop here. Thank you.